Okay, sorry about it. But okay, I need to restart again. Okay, just due to I forgot to record. Okay, let me see. Okay, okay, okay. For today, we discuss on the finite slope. Okay, so we have two type of analysis. The first one is the linear failure plane, and the second is the non-linear methods. Okay. So for the linear methods, we may refer to the linear failure plane methods. Okay. So actually, this method has been developed by Kuhlmann. Okay. Actually, Kuhlmann also has proposed another method for the retaining wall uh, to check for the stability of a retaining wall by using this graphical methods proposed by Kuhlmann. And there will be for the non-linear methods, okay, there will be a total stress approach, method of slices approach, okay. However, for today, I will only cover for the linear failure plane and also for the total stress for the non-linear methods, okay. So most probably next week, I will discuss on the method of slices, okay, either Filenius or Bishop's. Filenius and Bishop, okay. Okay. As usual, when we discuss on the slope stability, okay, so we need to determine what is the weight of the potential block that probably will move, okay. Okay, so for this case, okay, there will be two conditions, okay, when we want to use this linear failure plane. Okay, first, when we carry out for excavation and then we find out there are there will be a potential movement of block towards downwards, okay, based on a linear movement. Okay, so another one, during the constructions of embankment, okay, due to improper compaction methods or improper compaction work, okay, so there will be a possible of block movement, okay, at the edge of the slope, okay. So we need to determine the weight of this block, okay. From there, we can work out to determine what will be the driving force and also the resisting force, okay. So definitely for the resisting force, the force that prevent from the block to move downward, okay, while for the driving force, okay, the force that act the force that help the act for the block to move downward, okay. So based on the factor safety equation, okay, the resisting moment should divide with the driving moment, okay. So in that case, we need also to determine what is the length of this potential failure plane, okay. So this is the geometry, this is the angle of the slope, which is the beta, okay, while the potential linear failure plane is theta, okay, will be used in this calculations, okay. Okay. So from the figure, line AC is the trial failure plane, okay, the weight ABC, okay. So ABC, okay, AC is the potential failure plane. So we need to identify what is the weight of this block, okay, by using what we call as a triangular, an, I call it a non-irregular triangular shape, because there is not a normal triangle shape. Because if triangle shape, normally we use half times B times L, okay. But for this case, okay, so we need to use this kind of equations, okay. So half time gamma time L times H sine beta minus theta over sine beta. Okay, so that is the W value. Okay. Or you can look for any reference book, okay, to find to get the answer in terms on how to determine the W of the block. Means that the area. Okay, then we multiply with the unit weight. Okay. So the force that will cause the failure is, okay, T equal to W sine theta. So this is the driving force. Okay. Okay. So then for the resisting to sliding is given by, okay, RS over CD L plus W cos theta tangent phi D. Okay. So the factor safety will be, okay, so that is the one, that is the equation that we have seen before, okay, on the previous slide. Okay. Okay. So critical condition, previous that, okay, this is for a critical condition where we want to determine what is the critical height. Okay, normally we use this equation, okay, when we want to construct for a vertical cut. Okay, so vertical cut actually, okay, so for example, this is the top of the slope, okay, while this is the slope surface. Okay, so this is the toe. Okay, so this we call as a vertical cut. So we do a cutting, okay, which is 90 degree. Okay. So what is the allowable? What is the critical cut that we can make? Okay. Then we use this kind of we use this equation to determine the critical cut. Okay. By using this what we call as this equation, okay, by assuming that theta equal to b plus pi d over 2. Okay, so actually there are an explanation in das reference book, which is I already uploaded in the e-learning. Okay, by assuming the value of the factor safety, the value of the CDC, the value that there's some value that we assume as a 0. Okay, then we obtain the theta. Okay, we go later on. Okay, so then substituting theta, we get, okay, this kind of equation. Okay, okay. Then to determine the critical height, okay, so the H is moved to the left side while the rest is on the right side. So from there we can determine what is the safe depth of cut. Okay, and beta is the slope angle. Okay, so it depends. For example, if you want to construct for a vertical cut, so then we use 90 degree as the beta value. Okay, so same principle valid for condition where a slope consists of two layers, where the upper layer is assumed to slide along the interface between the two layers. Okay, so for example, if we have a two type of soil layer, okay, so the suggestion is to focus on the first layer, okay, because it's very tedious, okay, if we want to combine for both second and first layer. So that's why the most critical is on the soil layer at the top. Okay, so the soil layer is potential to move. And normally the layer of the top is less in terms of the strength compared to the second layer due to the stress acting on the second layer from the first layer. Okay. Okay. So that is for the linear failure plane. Okay. We will discuss later. Okay, by using several examples. Okay. So then we go for another method, okay, which is a secular slope failure. Okay, so this is a kind of slope failure, okay, either by using a manual calculation or numerical calculation, or by observe after a failure happen. So we may refer to three type of failure. Okay, so the first is the superficial, which is the erosions that normally happen on the slope surface. Okay, and then we have a shallow failure. Okay, and also we have a deep seated failure. Okay, so this type of failure is depend on the analysis, depends on the soil properties. Okay, and is the product from any analysis that we made later on, either by using a numerical or using a manual. Okay, the best is to use the numerical to determine or to use the software to determine uh, the type of the failure, either superficial, superficial or deep or shallow. Okay. Okay, so this is an example. Okay, the um, the the problem of this circular slope failure. Okay, we need to determine. Okay, for example, this case. Okay, where is the point of origin? Okay, to begin with. Okay, for example, this is the point of origin. Okay, so then we need to get all the information in terms of R. Okay, so if we are using the total stress, we need to get the information of the theta. Okay, so it's very difficult, okay, to determine where is the point or the optimum location of this center, okay, or the point of origin. Okay, so after we determine the center of or the center point, okay, then we may carry out for the factor safety analysis. Okay, okay. So from there, we determine the value of the factor safety. Okay. However, as usual, okay, so we need to determine the minimum factor safety value. Okay. So in that case, we need to shift the location of the point of origin to another location until we meet the minimum value of FOS. Okay, so that will be the optimum, what we call as the optimum location of the point of origin, and also that is the minimum factor safety value. Okay, okay. So, okay, this is an example, okay, on how to determine the point of origin, okay, by using the type of toe circle failure. Okay, so there will be three type of failure actually. Toe, where the failure start at the toe. Okay, so there will be a base failure. Okay, where it is enlarged, is more large failure, and there will be a failure produced at the slope or the slope surface. Okay, so for this type of failure, we call as a toe circle failure. Okay, so first we need to know what is the beta value. Okay, for example, if we refer to 33.79, okay, or 26. Okay, 26 is one vertical to horizontal. If I'm not mistaken, 33 is one vertical, 1.5 horizontal. If 45, 1. Okay. If 60 to 1, if not mistaken. Okay. Okay. So then, for example, if we construct the beta is 1 over 1.5 or 33.79, okay. So by using a protector, okay, so we need to draw another line, okay, which is where the degree is 26, okay. So we draw a line, okay. Nanti we draw a straight line, okay. Then make a horizontal line on at the top of the slope, okay. Then the actually sigma, so this is sigma, okay. Then the sigma 2, okay, should have a 36 degree, okay. So by using the same protector, okay, so we put as a 36, okay. Then draw another line, okay, until it meet the what we call as the line from the first, okay. So by using a compass, okay, so we should use a compass, okay. So the compass, we draw a line, okay, to show for it, to draw the rupture failure line, okay. But we need to make sure that this represent the same R, okay. So this is quite a tedious approach, okay? So although we have draw a line where this intersect the second and first line, however, when we draw when we use the compass to draw the rupture failure line, okay? So however, when we try to connect this point at the top to the point of origin, okay, the R is not similar, okay. So we need to repeat until we have the same R, okay. So that is a method, okay, where we can determine the point of origin, okay. Okay, sorry. I need to show for another example. They have two examples for this what we call as this to draw the point of origin. Okay, you can look on page 155 in Dr. Noli Gofar reference book. Okay. So this is the type of failure that I have mentioned previously. Okay, where we have toe, slope circle, base circle. Okay. So the first one that we have discussed previously is this kind of approach. Okay. So there will be another one. Okay, which is I guess this is much more easy to be used. Okay. So for example, we know what is the beta value. Okay, then we put the beta value. We use this graph, okay, to determine the XCH over H, and also XC over H, YC over H, and XC over H. Okay. For instance, if the degree of the slope is 30, okay, then we draw a line until it meet the XCH, okay, and move the line to the horizontal. Okay, for example, the value is equal to 1.5. Okay, then another one, which is to get the value for YCH, YC over H. So the value is equal to 2. Okay, when we refer to the Y axis. Okay. So let's say if the H value is equal to 1, we use this a simple calculation here. Simple example. Okay, 1. So the YC that we need to construct, okay, the height should be equal to 2 because 1 is the height YC over H is equal to 2. So definitely YC is equal to 2. Okay. So then we draw a line, okay, until it up to height, for example, 2 meter height, for example. Okay. Then for the YC over H is equal 1.5. Okay. Okay, because the H is equal to 1, okay, then the XC is equal to 1.5. Okay. By referring to the toe, okay, so we draw a line, okay, then the line should shift to the right side, okay, which is 1.5 distance from the toe location. Okay. So then from there, okay, we may determine what is the point of origin. Okay. By using a compass, then we draw the rupture failure line. Okay. So that is for the second method. Okay. So I guess the second method is much more easy compared to the first type. Okay. 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 For the first approach, which is the total stress approach. Okay. So we have two conditions here. Okay. Where the first condition, okay, there is no tension crack occur. Okay. So then, as usual, we need to determine what is the resisting moment. Okay, but for this circular method, okay, we're using a term of moment, not a force. The previous one we use the force. Okay, but for this case, because we are using, we drawing a circular or arch uh, shape. Okay, so it's easy for us to use the concept of moment. Okay, so for example, to determine the driving moment, okay, so we need to identify what is the weight of this block, okay, and then multiply with the moment arm. Okay, so W times D is the moment for the driving moment. Okay, while for the resisting moment, okay, so we need to determine what is the length of this failure block, okay, which is we note as LA, okay. So then we need to multiply with the strength under initial strength because we are using the total stress approach without any free value, okay. So the C we should time with the LA and also time with the moment arm of R. Okay, so this is the moment arm of R. So C equal to LA, C times LA, and then times of the moment arm of R. Okay, so that is the resisting moment. Okay, in logic, okay, the W is moving downward. Okay, so there will be a resistance that prevent from this block to move. So it's supposed to moving on the other side. Okay, so means that this will be a negative while this will be a positive. Okay, anti-clockwise is normally positive while clockwise is negative. Okay, so they get the factor safety value. Okay, the resisting moment over driving moment. Okay, that is for no tension crack. Okay, let's say if due to a proper compaction effort, okay, then okay, by due to the lack of the compaction effort, okay, So there will be a potential to have a tension crack. Okay. So tension crack, which allow water to enter this tension crack. Okay. So it made the length of the resisting moment will become less. Okay. So in that case, the new effective length, okay, will be reduced from the toe to the end of this we call as tension crack. Okay. Okay. So it may reduce. Okay. So how could we determine the new LA? Okay, we should determine the new alpha, the new theta. Okay. So by uh, by introducing a new theta, so we can get the new LA. Okay. So the same procedure for the resisting moment, CU, okay, times LA and also times R. Okay. Okay. For the driving moment, okay, so we need to count for the weight of this block, okay, then multiply with the diameter, with the distance of D, okay, and this tension crack, okay, by assuming that tension crack will be full by water, okay, so we need to include the hydrostatic pressure value in the tension crack in the driving moment. Okay, so this hydrostatic pressure in the tension crack, okay, will act as another driving moment. Okay, so there will be two combination of driving moment. First from the block of the slope and also from the hydrostatic pressure, okay, produced from the tension crack. Okay, so there will be also another potential, what we call as driving moment. Okay, if there are a surcharge on the top of the slope, okay, which is also located inside this failure plane. Okay. Okay. So there will be three potential of what we call as driving moment. Okay, first the weight from the block, okay, the hydrostatic pressure, and if there is a surcharge on the top of the slope. Okay. There will be an example discussed on this issue later. Okay. Okay. So this is the example. Okay. In terms of formula. Okay. So CU times LA times R. Okay. Over WD. Okay. So this is the formula. Okay. So to obtain the LA, okay, the equation is R theta. Okay. So that is the common typical equation to determine the distance of this LA. Okay. So R times theta, and the theta should be in radian. Okay. For example, if theta is 80, 80 degree cannot multiply with a normal number. Okay. So 80 degree should multiply with with pi over 180. Okay, then we multiply with R. So actually the equation for CU is CU R square theta. Okay, CU R square theta. So that is for the C. For the resisting moment. Okay, while for the driving moment, W times D. Okay, to determine the driving moment. Okay, for no tension crack. Okay, so if in the event of tension crack, okay, then LA is shortened and the hydrostatic pressure will act normal to the crack if it is filled with water. Okay, so if the tension crack filled with water, so we need to determine what is the effect of this tension crack towards the slope structure. Okay. So let's say if this tension current doesn't fill with water, so there will be no rho PW times YC. Okay. If the block or if the tension current has been filled half with water, okay, so we need to draw or to determine what is the new PW and to get what is the new YC. Sorry, YC. Okay, normally for a triangular shape, okay, when we refer to the top, the top as the origin for the moment movement, okay, so we need to use two-third of the height. Okay. Okay. And normally for retaining wall calculation, okay, because the base point is at the bottom, okay, so normally we use 1/3, okay, 1/3 from the height. Okay. Okay. So that is for the what we call as for the YC. Okay. So then YC multiply with the PW, okay, then plus the WD. While for the CU, we need to determine the effective LA, okay, which is LA prime times R, okay, to get the factor safety value. Okay. Okay. So we focus first on these two type of approach. Okay, for example, okay. I will refer to Dr. Noli Gopha example first. Okay. Okay. So for this example, so you can look at page 148. Okay, for assumption of linear failure plane, the soil mass is divided into the upper soil mass that we slide on the surface with the lower mass. The plane of weakness is assumed to pass through the toe of the field as shown in figure 5.2. In this figure, line AC is the trial failure plane. Okay, so we have seen this diagram in the previous slide. Okay, so this is the calculation, okay, to determine the W. Okay, so this is a typical way, okay, to determine the weight of the soil. Okay, but we need to do a slightly additional calculation to determine the L and also the H. Okay, due to the shape is not a normal shape of triangle. Okay, so a slightly different. Okay, where H over sine theta for the L. Okay, this is the L. Okay, and also for the H. Okay, for this H actually, okay, the H, okay, is equal to H over sine beta minus theta. And then we put all the equation, then we obtain W is equal to half gamma LH sine beta minus theta over sine beta. Okay, so that is for 5.13. Okay, so the force that will cause the failure is, okay, this is what we discussed previously. Okay, 5.15 is the resisting force. Okay, where CD is the developed cohesion. Okay, so then we may some of solutions, okay, for this type of failure. So we may use this equation, okay, which is the CD over C over Fs, okay, and also for the tangent phi d is the developed coefficient of friction. Tangent phi d equal to tangent phi over F S phi. Okay. So then the factor safety is will be, okay, CL plus W cos theta tangent phi, okay, over W sin theta. Okay. So means that they change, they include this in the RS, sorry, in this CD in the RS, and also the phi tangent phi d on the RS as well. So they obtain 5.16 K. So critical condition prevail that T is equal to RS. By substituting factor safety to 1 in the equation, we get, okay, means that RS is equal to W sin theta. Then rearrange for the CD on the left and the rest on the side. So we obtain 5.17. Okay. So the critical angle for theta can be determined by equating the first derivative of CD in equation 5.17 with respect to theta to 0, and solving for theta. The result is theta equal to B plus phi D over 2. Okay. So that is how they derive, determine the theta. Okay. Okay. Then substituting the theta in the 5.17, then obtain CD is equal to, okay, as shown in 5.19. Okay. Then rearrange to get the HCR on the left, so they obtain 5.20. Okay. So the H is the safe depth of cut, and beta is the angle of cut surface from horizontal. Okay. So same principle valid for condition where a slope consists of 2 layers. Okay. So this is what I've discussed in the slide previously. Okay. So we only consider for the movement of the slope on the top. Okay. Okay. Now we look for the example of 5.2. Okay. So this is cut through two source strata. Okay. The height of the slope is 5 meter and the height of the upper stratum is 3 meter. The lower stratum is highly permeable cohesive soil. Okay, the angle of the slope is beta is equal to 45 and the angle of the assumed failure plane is 30. Okay, the shear strength parameter at the interface of two soil is 7 and 25. The unit weight of the upper layer is 16.5. Determine the factor safety, again sliding. Okay, so the first thing is to determine what is the weight of this potential block failure. Okay, for the soil number 1. Okay, so L is equal to 6, H is equal to 1.1. Okay, so then we determine the W, which is equal to 54.4. Okay, then for the driving force, okay, T is equal to W sin theta. Okay, just include all the information or the input in the equation. Okay, and the same goes to the RS. Okay, then we obtain 64. Okay, the factor safety is equal to 2.35. Okay, it is a straightforward calculation. Okay. So for the problem 5.3, okay, a vertical cut is to be made through a soil mesh. Okay, so this is vertical cut. The degree is, the beta is equal to 90. Okay, so the soil has the following properties: 16.5, 25, 21. Evaluate the safe depth of the cut using a factor safety of 2. Okay, so we may use the HCR, okay, but we include the factor safety is equal to 2. Okay, but before we introduce the factor safety of 2, okay, we need to determine what is the new C after divide with 2 and new P after divide with 2. Okay, based on this equation. Okay. Okay. So in that case, C is equal to 25/2, which is 12.5, while P is equal to tangent 21/2, which is equal to 11. Okay. So then we include in the equation, okay, which is the critical height, okay, from the equation of 5.20, okay. Then we determine the value for the HCR is equal to 3.6. Okay. 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 Another example in 5.4, a 2-meter vertical cut is required for construction of trench. Okay, 2 meter. So the factors, the beta is equal to 90 because it is a vertical cut. The unit weight of the soil is 19, while its strength parameter are C 20.2 and Phi 28. Okay, calculate the factor safety of the cut with respect to both C and Phi. Okay, so the second example, okay, they provide the factor safety value, then we need to determine the HCR. Okay, while for the third example, they provide the height and then we need to determine the factor safety. Okay, so how could we determine the factor safety? Okay, so first, by using the HCR equation, so we already know that HCR is equal to 2. Okay, but we need to calculate, okay, to determine what is the C. Okay, so the C should okay, we should use the equation, okay, from 5.19, okay, which is the CD. Okay, so we need to calculate, okay, the CD, okay, by using the FSV and also FSC. Okay, so how does it work? Okay, first we need to use a try and error method. Okay, where first we need to assume the factor safety of Phi is equal to 1. Okay, then this tangent Phi D, okay, to get the Phi value. Okay, so tangent of 28, which is the one that provided in the example, 28, divide with 1 because factor safety is equal to 1. Okay, so tangent 28 of divide with factor safety, which is 1, so we obtain 0.532 for the phi d. Okay, so for vertical wall, beta is equal to 90. Okay, so substituting phi by phi d in the equation 5.20, then we get the value for the CD. Okay, so for example, gamma is equal to 19, this is equal to 2. 1 minus cos beta is equal to, what is beta? Beta is equal to 90. Okay, minus phi d is equal to 28. Okay, C beta is equal to 90, cos phi d is equal to 28. Okay, Then we do the calculation, we obtain CD is equal to 5.7. Okay, we already know that C is equal to 20.2. Then C divided with CD, we obtain the FSC is equal to 3.54. Okay, so then compare the result from the first FSC, it should equal with the FSC, but for this case, the FSC is not equal to FSC. So then we do for the second attempt, okay, by using F factor safety is equal to 2, okay, do the calculation, okay, then from the calculation, okay, we determine the CD value, okay, which is 7.30. Then the factor safety, the factor safety of C is 2.77, and it is not same with the factor safety of the fee, which is 2. Okay. The last attempt, okay, which is we put as a 3, okay, then we obtain 5D as a 10, okay, from the CD, we obtain 7.96, okay, from the FSC, C over CD is equal to 2.54, okay. So same, it doesn't show a same result as similar from the other example as a calculation. Okay, so it is enough to carry out for 3 attempts only. Okay, then we plot the relationship, okay, between the FSC and FSV. Okay, so we have 3 points here. Okay, why we need to do at least 3 attempts? Because if we use a 2 attempts, so definitely we will get a linear equation. Okay, but if we use a at least 3 attempts, so we can get either a linear and a non-linear equation, either linear or non-linear equation. Okay, then to determine the factor safety value, we should draw a line of equality. Okay, the intersection between the relationship with the line of equality is the value